Hey everyone, thanks for sticking around. I know it's the last talk of the session and everyone is tired. I'll try not to bore you. I'm going to talk about non-convex markets and pricing in these markets, um, which has a direct application in electricity markets. This is joint work with my amazing collaborator, Suyu, who is sitting in the crowd, DJ, and one of my two advisors, Adam Wierman. Okay, so there's a long history of markets being studied under convexity assumptions in economic theory, and convexities show up in all different contexts for cost functions, preferences, and sort of the main reason for that is that it makes things much easier, as we'll see an example of that. But really, the world is most of the time non-convex, and these non-convexities arise from many different sources. For example, if you have a startup or shutdown cost, that would make your cost function non-convex. If you have indivisibilities in your goods, if you have avoidable costs, or maybe just even the economies of scale is in a way that your cost function is non-convex. So they show up in all different practical applications. And these non-convexities really change how markets behave and how we should design prices in these markets. Sort of when we think about prices, we usually think about some constant per quantity thing that, basically the payments will be linear in the quantities, but it is well known that when the cost functions are non-convex, there may be no linear prices that support a competitive equilibrium. And it was suggested sort of as early as in the 90s or even 80s that we need to use price functions that's in these markets. And as I mentioned, sort of the key motivating example that I want you to have in mind throughout the talk is electricity markets. And so in this context, there's a market operator, or sometimes it's called ISO, Independent System Operator, that is trying to satisfy a certain demand from the consumers by buying that quantity from a whole bunch of suppliers. And the convexities here are in the cost functions of these suppliers. So traditionally, the way things have been done in these markets is that the operator assumes some convexity about these cost functions, and then because that causes a whole lot of problems, the generators may lose money. There's some sort of ad hoc side payments or uplifts that compensate for that. And these, I want to emphasize that different pricing schemes have a real impact in these markets, and in particular, in the past couple of years, there has been a lot of push for changing pricing formulations in these markets. And I don't know if the dates are, you can see them from here or not, but this is like from a couple of months ago that PJM, which is one of the main ISOs in the United States, has filed for changing the price formulation in their market. So it's a real problem that has a lot of impact in these markets. So in this talk, I'm going to basically tell you about how we should price in these markets. Okay? So let me tell you how does this market work. So like I said, there is a market operator. There's an inelastic and fixed demand D from the consumers. And this operator is trying to satisfy that demand by purchasing that quantity from a number of suppliers. And these are end suppliers of the same commodity. You can think of them all as all selling power in this case. And they have different cost functions, C1 through Cn, which again may be non-convex. The way the market works is the operator knows those cost functions. This is a standard assumption that, like in this literature, everyone assumes that's not the main problem. We're not doing a mechanism design problem here. I should emphasize that this is a pricing problem. So the cost functions are known, and the operator announces a whole bunch of price functions to these suppliers, or payment functions, if you will, which determines how much that particular generator is going to be paid for producing a certain amount of power. Okay, and then each of these suppliers make an individual decision for themselves to maximize their own profit. They can decide whether to participate in the market or not at all, and how much basically to produce. And so they're going to produce quantities Q1 to Qn, and hopefully the market operator's goal is to have a balance between the productions and the demand. So hopefully they'll sum up to D. And this is really the problem that the ISOs solve, like I said. So the key question and the key design question here is how to devise these price functions or payment functions. And the operator, like I said, is trying to come up with both the optimal quantities, the QI stars, and also the price functions that makes sure the suppliers produce that amount. Okay? So is the problem clear so far? Yes?
If the cost function is known, why the operator provides a range of quantities to choose?
Yeah, right. That's a great question. So you could do a dictatorial pricing, which will be very discriminatory, and that's the reason. So basically, there is an incentive for having prices that are close to uniform and price functions that are simple. I'll walk you through some simple example, and you'll see why that's not a desirable thing. So there is basically a desired property in this market is having price functions that are close to uniform. You don't want discriminatory prices for different generators. But that's a good question. So let's see what happens in the convex case, the so-called shadow pricing, the simplest case. Let's go through this simple example and see how things work here. So the operator first solves this convex dispatch problem, which is minimizing the total production cost subject to the load balance condition. And that lambda is the dual variable corresponding to the load balance constraint. And the optimal primal dual pair are QI stars and lambda star. In this pricing scheme, shadow pricing, this is the payment function you have. So it's a linear price and it's a uniform price. The lambda star is the same for everyone. This is not different for different suppliers. It's the same for everyone, and it is linear. So it's linear and uniform. The nice thing about this simple scheme, this simple price function, is that the socially optimal thing is a solution to individual suppliers' profit maximization problem as well. So that QI star, which is the solution to the socially optimal thing, is also a maximizer of the profit maximization, is a solution of the profit maximization problem of supplier I. And to see that, I mean, it's not hard to see because the CI is convex, that objective is concave, and so every stationary point of it is a global maximizer, and it's not hard to show that QI star is the stationary point of this problem. So that's basically what I wanted to emphasize here. And you can also show that this scheme, this lambda star times QI, has the lowest payment among all uniform linear price functions. So this is a nice property that it has. So basically, there are a whole bunch of properties that shadow pricing in the convex case satisfies. It clears the market. It minimizes the production cost. It minimizes the total payments. I told you this has the smallest total payment among all those price functions. It's revenue adequate, meaning that if the suppliers produce the socially optimal thing, they are not going to lose any money. And more generally, it supports a competitive equilibrium, meaning that it's in the best interest of the suppliers to produce the socially optimal value. And like I said, this is a simple and uniform scheme. It's linear and uniform. And finally, it's computationally tractable. It's very, it's a convex problem that it can be solved quite easily. This simple scheme breaks, the shadow pricing breaks for the non-convex case. And the reason for that is that this no longer holds. When the cost functions are non-convex, the socially optimal thing is not a solution to the profit maximization problem of individual suppliers. So the question is, can any of these properties be extended to the non-convex case? Can we have a scheme that satisfies these properties? And there have been a lot of attempts in the past decade or so. There are many pricing schemes proposed in the literature, some of which I'm going to briefly mention. So actually, let me start from the IP pricing, the integer programming, and sort of walk you through this one, and then I'll mention the others briefly. So this is proposed for the class of price functions that look like this. They have a startup cost with a linear plus a linear. So it should be clear that this is a non-convex cost, because if you connect this dot with any point on this line, the line segment between them lies below the function, so it's a non-convex cost. And the way IP pricing works is it formulates the dispatch problem similar to the shadow pricing, so minimizing the total cost subject to the load balance condition. Oops. This is a mixed integer linear program this time. You can attempt to solve it with off-the-shelf solvers. I mean, it's an NP-hard problem in general, but nevertheless, all these solvers solve NP-hard problems all the time. So that's what you can attempt to do. And then you impose the, you basically set the integer variables to their optimal value that you obtained from this, and you solve a linear program now. So you take that mixed integer linear program, fix the integer variables, and solve the linear program now. That gives you the dual variables lambda star and ui stars, and the payment would look like this. Again, it has a linear uniform term plus an uplift term, which is paid only if the generator is actually producing. So if the generator is participating in the market, that it's going to be paid. The properties that this scheme satisfies, so it supports a competitive equilibrium, it clears the market, both the total payment and the total costs are minimal, and it's relatively simple and interpretable. But the problem with that is that it doesn't extend to general non-convex costs, and it also relies on these off-the-shelf solvers for solving NP-hard problems. So if I want to summarize, so this was the shadow pricing. It satisfies all these properties. It works for convex. This is the IP. Again, it satisfies all those properties, but works only for this particular kind of non-convexities. I won't go through the other schemes in the interest of time, but let me show you the summary of all these different schemes. Right. So basically, all these different schemes are specific to special kinds of non-convexities. They assume some form of cost function, and they're specific to that. And they also lack some of the important economic properties. And most importantly, they're not economically efficient because the payments can be very high. They're minimizing the costs, but the payment, which at the end of the day, what is the operator cares about, can be very high in these schemes. So can we come up with a systematic way of doing pricing for general non-convex costs? Turns out that you can do so, and that's what we propose. It's also called EC pricing. That's just a coincidence. We didn't mean to steal the acronym. But so let me tell you how it works. We minimize the total payments directly instead of minimizing the total costs. And we simultaneously minimize over the quantities and the price functions. And these price functions are constrained to be in a set of desired price functions, which can be, for example, linear plus uplift. It can be piecewise linear with 2 pieces, or piecewise linear with 3 pieces, or so on. And we are going to impose all the equilibrium conditions as constraints here. And namely, again, market clearing, revenue adequacy, which basically means the suppliers don't lose any money by producing the socially optimal thing. And it's in the best interest of the suppliers to follow the dispatch, this competitive equilibrium. So like I mentioned, this allows flexibility in the form of price form. It directly minimizes the total payments. It optimizes jointly for the allocations and the price functions. And we enforce the equilibrium conditions as constraints. And again, this is general. This is not specific to any class of cost functions. There are a number of questions that may come to your mind. When you see this, you might say, okay, you have imposed almost all the desired conditions as constraints. Does this even have a solution? And yes, it turns out that there always exists a class of price functions for which this has a solution. And the other thing is what happens to the total cost. We're just minimizing the total payment. It's not hard to see from this constraint and the objective that okay, I'm running out of time. I should speed up. But so basically, the total cost is also bounded. I'm not going to go through the details of the analysis, but let me give you the results. So you can find an epsilon approximate solution to that optimization problem I showed you in time that is polynomial and even linear in n and polynomial in 1 over epsilon. And I should emphasize that these two numbers, L1 and L2, don't scale with n. They're small constants. So that's the results. This is linear in n and polynomial in 1 over epsilon. And I should just mention that in the epsilon approximate definition, we basically guarantee exact load balance. And the profits are relaxed by an epsilon, so that's not of a major consequence. Let me wrap up quickly. I won't go through the details. Again, you can check out the paper for the details of the algorithm. And I just want to mention that this extends to the case of network markets, which to the best of our knowledge had not been considered in any of the previous work. And with that, so I showed you, basically we proposed a pricing scheme that satisfies desired economic properties for general non-convex costs. It comes with a computationally efficient algorithm, and it applies to network markets. We're doing some experiments in the electricity market, and there are a lot of results in the paper you can check out. Hopefully we can convince the operators in the next couple of years or so to adopt the scheme. And with that, I'll stop here.
So this kind of a meta thing here, I really like the approach, of course.
Thank you.
But you know, if you go with this type of thing, there's really much less incentive for capacity investment. So are you thinking that this would be somehow combined with some sort of explicit capacity subsidy for producers to actually buy capacity to make electricity?
Right, so that's a good point for long-term planning and sort of incentivizing long-term participation. So that's something that can be potentially combined with this scheme in a way that I think that's cool. I mean, we have some variations of this scheme in the paper too, that it can be taken care of, I think.
Let's take the rest of the
Okay.
questions offline
Okay.
and I go with